In the previous module, we introduced kind of the framework of generalized linear models, and one of the things that was said was that the mathematics work out really well for a special class of distributions called exponential families. And so in this set of notes, we're going to look at what an exponential family is, we're going to look at some special cases, and see what makes them so attractive to work with. So we're going to start out by just defining an exponential family. So previously we saw that the random component of a GLM consists of a random variable y with mean or expected value of y. We could denote the observations as a vector. And standard GLMs treat y1 through yn as independent. And so we're going to look at a class of distributions called the exponential family of distributions. And we're going to start by defining a single parameter family, exponential family. So a distribution falls into an exponential family if its PDF or PMF can be written as follows. And one thing that I really want to emphasize here at the beginning is that the notation for exponential families will vary from source to source. And so it's important when looking at them to really see what the individual components are and not to get so stuck on the exact notation that was used. So if we look here, what I really want you to notice is if the parameter we're interested in is theta, and then we also have y. Notice what we have here is we're really splitting the PDF into a couple different components here. We've got a component that's in the exponent. And in the exponent, we're going to have some function of the parameter times some function of y. And then outside of the exponential, we have a function of the parameter and a function of y. And if we can get our PDF into this format, it ends up that q of theta, this is what we call the natural parameter. The other three functions, these are just arbitrary functions. They'll change from distribution to distribution, and they're not all that important. Now, when t of y is equal to y, we have what's called a natural exponential family. And we're going to primarily work with natural exponential families. And so just to kind of illustrate what I mean by the notation is we're going to look at a couple different formats how this could be written. So the first one, we're going to write out what this would look like for a natural exponential family. So a lot of times, like if you went to Google and you just looked up what is a single parameter exponential family, you might see something like the following. And so notice that the function of y has just been replaced with y itself. And so again, this is what we call a natural exponential family. These are really common to work with. Having the t of y there, that just makes it even more flexible. So for example, if you go to Wikipedia and you look up exponential family, you are going to see a function of y there. I think Wikipedia might use capital A instead of capital T. But again, the idea is we're going to mainly be working with natural exponential families, so we're just going to have the y there. Now let's look at some other ways that we could write this though. So keep in mind that the functions a, b, and, well, now we don't have the t, it is gone. A and b are just arbitrary functions. And so for example, I could we'll define a new a theta, we'll call it a star of theta, and let it be equal to the exponent of negative a theta. And if I define the function this way, then I could write the exponential family as follows. And so this is another common way that you'll see exponential families written. And so again, you'll notice we really see what we had before. We've got a function that's just of y, a function that's just of the parameter, and then we still have that q of theta, or the natural parameter, times y. And then we'll look at one other way that these are commonly written. We could also write this as the following. And so notice all I've done here is move the b into the exponent, so I'm calling it b star because the function has slightly changed, just like I did with a in the other way that we could write these. So again, all of these are common ways to write out an exponential family. Whatever resource you look at will use probably one of these three things, but what you'll see change a lot is whether they call it A or B or C, or they'll have some other letter there. The important thing to realize is really what you've got here is you've got a function of the parameter you're interested in multiplied by y, because again we're going to focus just on natural exponential families, a function of the parameter, and a function of the data. Okay. These two functions, the one just involving the parameter, the one just involving the data, it doesn't really matter if they're in the exponential. They can be outside multiplied like you see in the first form, but that y times q of theta, the natural parameter, we do want that one in the exponent. And so I've got a note here, the representation can be written different ways and can be slightly generalized, but the above definition is sufficient for all commonly used GLMs. So as we see, if a distribution can be written in this manner, maximum likelihood estimation and inference are greatly simplified and can be handled in a unified framework. And so let's just look at some examples of how we can show that something is in an exponential family. So we're going to start out here with the Poisson distribution. And so here I've got the PMF of the Poisson distribution, and I've parameterized it using mu. So first thing I'm going to do here is just rewrite out my distribution. And what I'm going to do is notice here that I've got mu y in the numerator and y factorial in the denominator. What I want to do is I want to separate all of the terms out so that they're multiplied by one another. So I'm just going to have this equal to e to the minus mu 1 over y factorial mu to the y. And the reason I want to do this is if I think back to the form that I'm trying to show it in, I know that there's functions that are multiplied throughout, so this might help me see things easier. Now, the next thing I want to do is just look at my terms and see what they are functions of. So notice this first term is just a function of mu. Notice this next one is just a function of y, and this next one is a function of mu and y. So looking at this, I know that that q theta times y, that's probably going to come into play with this last term. I'm going to have a function of just y and a function of u, or mu rather. Now, the function that involves both y and mu, ideally I would like that in the exponent. So notice here that if I take the exponent of log mu y, that is going to be equal to the exponent of y log mu. So now we can rewrite, and we have the following. And so thereby this is an exponential family with the following. So here we have a of mu is equal to e to the minus mu, b of y is equal to 1 over y factorial, and q of mu is equal to log mu, and this is what we refer to as the natural parameter. So at this stage, these two really aren't that important. The one that we're really concerned with is this natural parameter piece. All right, let's look at another example. So suppose next we have a binomial distribution. And in particular, we're going to consider the binomial distribution when n is equal to 1, i.e. a Bernoulli. And here, n is going to be known. So we're going to do the exact same thing. So if you want to, this would be a really good time to kind of pause, maybe play around, see if you can show this is in an exponential family, and then come back and see if you get the same thing that I do. All right, so starting out here, I'm going to simplify this since n is known. I'm just going to write this as f of y given mu. You can include the n here as well. I'm just going to, just for ease, leave it off. And if I look up here at what my distribution looks like, I've got several things. I've got a mu and a y together here, and I've got mu and y's together here. So what I'd like to do is let's just go ahead and put everything into the exponent to start with. So using that same trick as before, we're going to take the exponent of log mu to the y, 1 minus mu to the 1 minus y. And now this is going to be equal to the exponent of y log mu plus 1 minus y times the log of 1 minus mu. And now I notice here that I've got y times some function of mu, but I've also got y times some function of mu over here, so I need to expand that a little bit further. Okay. And now that this is expanded, I notice that I have this term right here. And notice what this is this is y times a function of mu. And then I have a function of mu out here. And I don't have a function that's just of y by itself. So then I can take this 1 minus mu out of the exponent. And then we have an exponential family. So notice in this case, a of mu is going to be equal to 1 minus mu. B of y is just equal to 1 in this case. And then q of mu is equal to log of mu over 1 minus mu. And again, this is the natural parameter. All right. So it's often helpful to be able to work with a distribution that has a second parameter. So think like a normal distribution. We're often interested in the mean, but we also have sigma for the variance. So what we're going to define next is what's called an exponential family with dispersion, or an exponential dispersion family. And so it falls into an exponential dispersion family if the PDF can be written as follows. Okay, so a couple things to note here compared to what we just looked at. First of all, notice that this does have an A, a B, and a C. These are not the same A, B, and C as what we just saw with the exponential family with a single parameter. Remember that we just used A and B to be arbitrary functions here. So the B that you see here is not the same B that you saw previously. So keep that in mind. These are just arbitrary known functions. Now, when we write things as the exponential family with dispersion, often what you will see in the notation is that the q of theta gets dropped and is now just denoted as theta. So you still have y times a function of the parameter here, but now we just denote that function as theta. And so that gets a little bit confusing, but what we're going to do is we're going to look at the Poisson distribution under this type of exponential family, and I think that will help. Now notice we also have that second parameter here, and phi is what is called the dispersion parameter. So what you'll see is if you're working with a normal distribution, for example, phi is going to involve sigma and theta is going to involve mu. All right, so it ends up that when phi is known, this simplifies into the form for the natural exponential family with a single parameter. And so let's look at why that is true. So the first thing I'm going to do here is write out the distribution. Okay, so note that if phi is known, then any function of it is a constant. And so effectively what happens is these pieces where these functions involve phi, they're going to be constants, and so they just kind of get lumped into one of the other functions. And so what happens is this distribution now becomes the following. You're still going to have y of theta minus b of theta, because those both concern theta rather. But you're no longer going to have this divided by a of phi. And the reason for this is a of phi is a constant. So for example, let's just say that that constant was 2. What would happen is that 2 would actually get grouped in with the b function. And remember that theta here is a function as well, so that 2 would get lumped into this function. And then here you have c of y and phi, but again phi is known, so it's a constant, so this just becomes c of y. And so this isn't to say that the theta, the b of theta, and the c of y are the exact same forms as they are up here, but you do have a function of theta times y, a function of theta by itself, and a function of y by itself, and so you're back to having that single parameter exponential family. And so just like before, just a note here on notation, if you look at different resources, the notation is going to look different. Now, one thing that I do want to note here is in this form right here, this is going to be the form that we work with when it comes to getting estimates for the parameters and looking at distributions for the GLMs. This is the specific format that we are going to work with. So in what follows, I am going to reference thetas and b of thetas. So the b of theta format does matter here. So in the pages that follow, when I mention b of theta and y of theta, it is for this specific format. And so for that reason, when we get into actually looking at the estimates in the next set of notes, everything is going to refer back to this format. If you look at other materials or other sources, you might see slightly different notation, or the formulas might look slightly different, and that could go back to which format of the exponential dispersion family they are using. So keep in mind that this b of theta, when I reference b of theta later on, is the one that I'm going to be talking about. All right. So let's look at an example of this, and we're going to look specifically at the normal distribution. So here we have our PDF. So let's see if we can write this in the format of an exponential dispersion family. Okay. So the first thing I want to do is, if I look at my format for the exponential dispersion family I'm going to work with, I know that everything is in the exponent. So I want to get these terms into the exponent, and I can do that using a log. Okay, now I have everything in the numerator. Probably not in the numerator, but in the exponent. So the next thing I'm going to do is, I know that if I look at my format of my exponential family up here, what I would like is a function just involving y some function involving mu minus some function involving mu divided by something involving the dispersion parameter, which in this case will involve sigma. So I want to try to get it in that format. So looking up here, what I can see is, I've got a y squared, I've got a minus 2y times mu, and I've got a mu squared, and I've got a 2 down here. Really what I would like to have is I would like that single y by itself times some function of mu, but I've got that 2 in the way. So next what I'm going to do is bring that 2 from the denominator up into the numerator. And then last, remember what I really want here in this first piece divided by sigma is I really want, y times some function of mu and then just a function of mu. I don't want this piece that involves y squared. So I'm going to move that over. Sorry, I'm running out of space here, but that's minus log sigma square root of 2 pi. And notice the reason that I don't have that in the denominator is since it was in the denominator here, I switched the positive to a negative. All right, so therefore we have an exponential family with the following. Theta is just going to be equal to mu. Okay, so that's our natural parameter. B of theta is going to be equal to 1/2 mu squared. A of phi is equal to sigma squared, and C of y and phi are equal to 1/2 y squared over sigma squared minus the log of sigma times the square root of 2 pi. Now, pieces of this that we're going to care about. We're definitely going to care about the natural parameter later on. And then, since we found B of theta using this format, all the way back up here, this format for an exponential dispersion family, this B of theta will actually come into interest later on as well. So those are the two pieces that we really care about. All right, let's look at one more. So we saw that the Poisson distribution belonged to a single parameter exponential family, but for using the estimation techniques that we are with GLM, it is also going to be useful to show that it belongs to an exponential dispersion family where phi is equal to 1. And the reason for this is if we use that format of the exponential dispersion family or that way to write it, we're going to get the natural parameter and we're also going to get that B of theta, which is going to be useful later on. So here, very similar to what we did before. This time I'm just going to go ahead and put everything up in the exponent because I know for this exponential dispersion family, that's how I'm writing these. So notice here we have y times some function of mu. where mu is the mean of the Poisson distribution. Remember that theta can be a function of the parameter that we're interested in. So let's let theta be equal to log mu. And we're going to let a of phi, oops, that's an A, be equal to 1. Notice we could rewrite this as the following. Actually, let me So now writing it this way, we could see the following. Theta is equal to log mu, and that is the natural parameter. B of theta is equal to e to the theta. A of phi is equal to 1, and c of y and phi is equal to negative log of y factorial. So again, the pieces that we're really going to care about are these two. So let's go back to on the previous page where we already looked at the Poisson distribution. So back on page 2. So notice here, using the exponential dispersion family, we had the natural parameter was equal to log of mu. So let's go all the way back up here. Notice that that was the same log mu that we got. Now, using this format of the exponential family, I told you, don't worry about b. We don't really care about it, and that is true. We don't care about the b of y when we format it that way. But when we format it in terms of an exponential dispersion family, we do care about the b function, and so in the next set of notes, that is going to become useful. So just keep that in mind. So once you show that something belongs to an exponential family, what you really want to do is show that it belongs to an exponential dispersion family, even if it's a single parameter one, because in these cases a of phi is just going to be equal to 1. And the reason for it is if we put it in that format, we are going to get two useful pieces of information. All right. Oh, sorry, that was for the normal. For the Poisson, these are the two useful pieces of information. Didn't go down far enough. All right, so we talked about the score function when we looked at MLEs. Now let's talk about the score function for exponential families, and we're going to see why that b of theta is useful. So as we've seen, maximum likelihood revolves around the score. So consider then the score for a distribution in the exponential dispersion family. And so we know that the score is going to be equal to the derivative of the log likelihood. So the first thing that I've done here So I am going to fix this in your notes. I just saw an error here. So let me just erase parts of this. There is no by here out front, so this will be fixed in the notes that you all have. Yes. All right, so again, I will fix that in your notes, so just sorry about that. All right, so if we start out here, let's write out what an exponential dispersion family looks like. So the format we're using is this one right here. So if we wanted to find the log of that, or probably the likelihood of that, it's just going to be the same thing. Now remember here, if we had multiple y's, we would look at the product over those y's, but here we'll just assume we have a single y we're looking at. And then to find the log likelihood, we would take the log of the likelihood, and then if we're taking the log of the exponent, notice that that just leaves us with this piece right here. So this piece right here is the log likelihood. So we know that the next piece we want to do is take the derivative with respect to theta. And so notice here a of phi is going to be a constant. So if we take the derivative with respect to theta, we get the following. So this is, pardon me, the score function when you have an exponential dispersion family. And so notice here we've got that b of theta function in here. We also have the a of phi, but the b of theta is going to be the more important piece. So recall from the and part of the reason for that is, I should say, most of the distributions we work with are going to belong to the exponential family with a single parameter, so think like binomials, Poissons, pardon me. And then we already know from the previous module these two pieces involving the score function. So for distributions in the exponential family, it can be shown that the variance is equal to the following, and we get the following pieces. So notice that the expected value of y is actually equal to the first derivative of that beta function, and we can show that the variance is equal to a of phi times the second derivative. So let's look at this for a Poisson and see if we get what we would expect us to. So on the previous page, we had b of theta, if we go back up here, is equal to e to the theta. So the first thing I'm going to do is take the derivative of b with respect to theta. Well, that's just going to be equal to e to the theta, and then the second derivative again is just equal to e to the theta. So now let's use this to find the expected value of y. So notice the expected value of y in this case is equal to e to the theta, but, and here's the trick, remember that theta is equal to the log of mu. And so this is equal to e to the log of mu, which is just equal to mu, and we know the mean of the Poisson distribution is equal to mu. Now what about the variance? So in this case, if we want the variance of y, we know that's equal to a of phi times the second derivative, but remember for the Poisson distribution, a of phi is just equal to 1, so this is going to be equal to 1 times e to the theta, but again, theta is equal to theta is equal to log mu, so that is just equal to mu. And we know for the Poisson, the mean and the variance are equal to one another. And so what is happening here is the variance of y depends both on the scale parameter, a constant, and on b, a function which controls the relationship between the mean and the variance. And so it ends up that for a normal distribution, that second derivative is 1. In other words, the mean and the variance, they have no relation. And we know that about normal distribution. For the Poisson distribution, the second derivative of beta is equal to theta. In other words, what that does, that should say e to the theta. What that does is the variance is going to increase with the mean. And then similar for the binomial distribution, and I'm going to actually fix this right here in your notes, so look for that on the actual printout that you have. The variance is going to be largest when theta is equal to 1/2, and it decreases as theta approaches 0 or 1. All right, so now let's talk a little bit more about that natural parameter and the canonical link. And so I've got a section here. It says recall the link function is the function of the expected value of the random variable e of y, and it's usually identified by the Greek letter nu. So in principle, g could be anything, but it ends up that the link function that transforms as a means to the natural parameter is what we call the canonical link. So in other words, it ensures that the systematic component of our model is modeling the parameter of interest, sometimes called the natural parameter, in the distribution. There is therefore a reason to prefer this link, the canonical link, when specifying the model. And so it ends up, it has some really nice properties that I have listed for you here. And so, for example, we could look at what's the canonical link for the binomial distribution. So if you go back and you look at what we had for the natural parameter for the binomial distribution, we had the following. So what we can do is we can use this to help us determine what the appropriate link function is. So what we do is we set nu to be equal to g of ui equal to that natural parameter. And then what we can do is we can back transform to get the following. And so this is exactly when we looked at potential link functions before for the binomial last week, one that made sense. So all right, so that concludes this note set. In the next note set, we're going to look at how we can use this information to help us start making estimates for GLMs.